So I just received a message of some technical issue on the Google Meet. So some of you might get will be gone out of the session, but you can log back in. So maybe we have to wait a minute. There's a technical issue.
Yeah, please bear with us. Thank you.
Okay, seems to be fine. And if any of you got out of the, and of course I can't tell them because they are already gone right now. But yes, some of them, if now go out of this meeting, please come back. You should be able to come back again. So I give over the chair to the Sugunakar, and the speaker is Simon, who is a very active cheminformatician in Freiburg. Go on, Sugunakar.
Yeah, thank you so much, Kiran. And I welcome all the participants once again. And Simon, to this wonderful Galaxy workshop. To brief, Simon Bray is a member of European Galaxy team at University of Freiburg. And he's basically belongs to a bioinformatics group, Department of Computer Science at University of Freiburg, Germany. He's basically interested in computational chemistry, molecular dynamics, and the use of workflow management systems for virtual screening. He's been part of popular Galaxy Chemical Toolbox. He's finishing his PhD from the University of Freiburg, but he has got extensive knowledge in protein-ligand docking and cheminformatics. With these few words, I welcome Simon to take over the session. Yeah, thank you, Simon. Yeah, please, the stage is yours.
Okay, thank you very much for the introduction. So I will try and share my screen.
Yes, you can.
Yeah, please.
Let's see. Okay. And I assume that you can hear me okay? I don't need to make any adjustments
Yes.
to the microphone?
You're audible enough.
Okay. Great.
Yeah, you're audible. But could you please a bit louder? Thank you.
A bit louder, sure. Is that better?
Yep, it's perfect.
Okay, great. Okay, so then I guess I can start. So first of all, thank you very much for the invitation to present this workflow about protein-ligand docking. So as was already said, my name is Simon Bray. I'm a member of the European Galaxy team at the University of Freiburg. You already heard a lot about the various tools and workflows for computational chemistry in Galaxy from Chris. And the idea of this part is to give you some kind of practical experience of how you can do these kind of analyses yourselves in the Galaxy platform. So I guess most of you have some idea about what this technique is. It's a molecular, it's a modeling technique for predicting the binding position of small molecules or ligands within a protein binding site. So the idea is that you have a particular protein which is of interest that you want to study, perhaps because it's implicated in some condition, and you would like to find some small compounds which can bind to it effectively and therefore change the behavior of the protein and therefore target the condition. So the idea behind this protein ligand behind this this technique is that you have a list of compounds, a compound library, and then for each of these compounds, you predict the best possible binding position of the ligand within the protein binding site. And this procedure is not something which can take place by itself. So
Simon, we lost you. You still hear us? Looks like he has a technical issue.
Shaman Bray, are you there?
Okay, I'll try to contact him. Okay, you can hear us.
Yeah, please.
Probably you might need to rejoin, Simon, or I don't know if you have an issue. We can't hear you as of now. That's what the status. Okay, let's hope he will be rejoining.
Yeah, please, Simon. Yeah, please go ahead. Simon, sorry, we are not able to listen. Just
Now?
yeah, it's fine now.
Okay. Yeah, so you might want to continue on to some additional steps. So some MD simulations or some free energy calculations. But the idea of this tutorial is just to do some basic protein ligand docking to give you some idea of the basic tools which are available in Galaxy for cheminformatics and computational chemistry. So I guess in the last that today, in the course of the various workshops that you heard and presentations, you already heard a lot about Galaxy, so I don't want to repeat too much here. But one point which I would like to emphasize is that it's a workflow management system. So it allows you to build quite complex workflows within this graphical interface, and then to run them at a high throughput level. So you can run them also on the command line once you have a well-developed workflow which you trust and you're happy to run on a library of 100 or even 1,000 compounds. We have this specialized web server, cheminformatics.usegalaxy.eu. So yes, you can see the screenshot here. It contains almost 100 different tools for computational chemistry and cheminformatics analysis. There's also quite a range of different tutorials on the website of the Galaxy Training Network, which I guess that you saw already. Today, we will do a relatively simple tutorial. But if you are interested in doing a more advanced topic, then we also have a video tutorial for high throughput molecular dynamics uploaded onto YouTube. If you want to go through this perhaps later on and get to know some more advanced tools and some more advanced concepts in Galaxy, like how to run workflows from the command line, how to organize data into Galaxy collections as well. And the system that we'll be looking at today is the N-terminal domain of the heat shock protein 90. So this is a chaperone protein, a protein which is existing in the fold.
Simon, are you there?
Simon, we can't hear you. Okay, I will try to reach him out if there is any problem.
Yeah, please bear with us because of some technical issues. We'll be coming back soon.
Yeah.
Thank you.
So I should be back. I should be back now. I hope
Yeah,
you can hear me.
thank you, Simon. Yeah.
Yeah. Yeah, sorry about this. I just had some connection issues. So yes, I hope that you heard that I was talking about the protein that we'll be looking at during this tutorial. So the N-terminal domain of the heat shot protein of this heat shot protein. It's a chaperone protein which is implicated in some kind of cancer, and the idea is that if you can somehow block the activity of this protein, then you can slow down the process of protein synthesis, and therefore also slow down the process of cell growth. But the really important thing from our point of view is it's a simple globular protein which has a clearly defined binding site. So you have this beta sheet structure at the back, these alpha helices, between which you have this binding site where you have an example of a dot ligand shown in this diagram. And if you want to read more about it, then there's quite a nice review paper, quite old, from 2006, but still a good introduction to the HSB90 structure. Yeah, so that was all I wanted to say in terms of the introduction. Now I will go to the Use Galaxy EU platform and show you some of the tools which we'll be using. So please feel free if you're able to log on to usegalaxy.eu yourself. I think you have a link for joining the training, and you can follow along the steps as I demonstrate them. So I'm not sure if you saw this training icon already, but you can click on it, and it brings up this this window in the center of the page. So I have it already on this Protein-ligand docking page, but if you're on this page here, then you can click onto Computational Chemistry, and then onto the link here. Yes, so there's some introductory text and a little bit of information about the protein, which I already told you a bit about, that it's a chaperone protein responsible for helping with protein folding. And so the first step is to download a protein structure. So I guess that you know already that probably the most common format still for recording protein structures is the Pdb format, and there's the protein data bank where protein structures are recorded. We have a tool also in Galaxy which allows you to download structures from the PDB based on their accession code. So in this case, this is 2BLC, the accession code, which is associated with a particular crystallographic experiment that was done on the HSB90 protein. And so to download this protein, then you can just click on this Get PDB icon. And yeah, this is a very, very simple tool. I guess you used tools which are a lot more complicated so far today. And you just enter in the accession codes, in this case, 2BRC, and start the job. So yes, I'll give my history also a better name. And we wait for it to load in our history. Okay, so now the job starts to run. And we can think already about the next steps. In this Pdb file, then you have various different structures. So you have the protein itself. You also have a small molecule. So this molecule here, which is bound in the center. And in fact, I can show you that with the NGL viewer, which is embedded into Galaxy. So to get to this page, you can click on this visualization icon here. You have these options here, and you click on NGL viewer, and it takes some time to load. But you see this view of the protein, so similar to what I showed you before with these beta strands at the reverse of the protein, and then these helices at the top, and in between you have this structure here. And what we want to do is we want to remove the ligand, or rather separate the protein and ligand into two separate files, so we can then dock some new compounds which we will select into the binding site of the protein. So for that, as is described in the training material, we use this grep tool. So you can either click here, or you can search for grep in the tool panel, and it's this tool here. So search in text files, grep, and we first search for lines in this file which match the regular expression, het atom or heteroatom, so the atoms of the ligand. And I press that then on execute. And I run the same tool once again. But this time I change match to don't match. So I have one file which contains all the atoms of the ligand, and one file which contains all the rest of the atoms, so the atoms of the protein. Oh wait. So actually, this first example was a mistake, because the heteroatoms will also include the water molecules. We should instead search for the regular expression CT5, which refers to the code which the ligand is referred to in the structure. So yes, so I'll just remove that data set and then try once again, like this. So I have, so I hope that wasn't too confusing, but I have this first data set here, which will contain the coordinates of the protein. in Pdb format. So it will include all of the atoms which are not labeled as heteroatoms, and this file will then contain the coordinates of the Pdb. Exactly. Oh yeah, and this is also not correct because I need to use the original Pdb file which I downloaded, and not this file. So yeah, I'll try this again. But then, so you see that in this ligand Pdb file, we can also inspect the contents. That we have a list of all these lines in the file which are labeled which labeled het atom, and in this column you have CT5, which is the name of the ligand code. We can also view this in the VMD viewer, and you can see the structure of the ligand. So you have this resource null structure here, and these 4 different rings which are connected. So yes, I expect that was quite confusing to see, but it should be explained correctly in the tutorial. So in the first step, then select lines which don't match a heteroatom, and then rename the dataset protein Pdb. And then in the second step, select lines which match this CT5 ligand code. Then this will be the ligand Pdb file. Exactly. I can also rename this protein Pdb file in the meantime. Exactly. So now I can visualize also the protein Pdb file, and you should see that the structure has now been cleaned. So the ligand has gone from the binding site, and we can start the tutorial once we have our prepared data sets. So yes, maybe I'll stop now for a couple of minutes and wait for you guys to catch up if you were if you didn't reach this step so far.
So meanwhile, if you have any questions, also you can ask.
Please do raise the hand otherwise.
Oh yeah, thanks for posting the link. Also in the chat to the training. Yeah, so perhaps I just continue. There don't seem to be any questions, and I think it wasn't too complicated so far.
There seems to be probably a question. Binta Fazis,
okay.
you want to ask any question? Okay, yeah.
Yeah, there's a question like oligosaccharides and monomers is same when we use it as a ligand.
Yeah, I don't fully understand. I'm afraid. Can you provide a bit more detail?
Yeah, Binta Varghese, like, could you please unmute yourself and talk? Yeah, you can talk. You can unmute and you can talk. I would have been the given rights.
Okay. Yeah, I guess that I will continue.
Yeah, please go ahead, sir.
Yeah, I will do. Right. So then, so in this tutorial, then we want to look at this idea of preparing a compound library. So it's a list of chemical compounds that we then can dock into the protein binding site. And so to process the compound library, then we use a tool which allows us to download compounds from this Chembor database. And the first thing that we need to do is to convert our ligand Pdb file into the so-called SMILES format. So we can use this compound conversion tool for that. So we take the ligand Pdb as our input file, and as output we select SMILES format, and the rest of these options we can leave as the default options. So yes, I'm not sure how familiar you are with different file formats for representing chemical compounds. So already we saw this Pdb format, which provides the three-dimensional structures or three-dimensional Cartesian coordinates of molecules, and the SMILES the SMILES format provides representation of molecules as strings. So it doesn't provide the three-dimensional coordinates themselves of the atoms, but just but it just shows as a kind of molecular graph how the atoms are connected together. So once this tool completes, then I guess it'll be easier to see that. So I'll rename this data set to ligand SMILES, and let's see exactly. So if I press on this view data icon, then this is what the SMILES string looks like. So you have different symbols which represent different atom types. So obviously C is carbon, O is oxygen, N is nitrogen, so this is a way of representing as a single string the same the same compound that we saw here. And we need the SMILES format for the next tool, which is this Chembor search tool. So search Chembor database for compounds which are similar to a SMILES string, and we can then select the SMILES input type. So we could either enter the SMILES directly into this form here, or we can select file and insert this data set which has just been created. Then what this tool will do is it will search the Chembor database for tools which are chemically similar to this compound here, which we've extracted from the protein data bank structure. And this Tanimoto Cutoff Score is a kind of similarity threshold. So a high score means that it will only return compounds which are similar, and then a lower score means that you will get a wider range of compounds which are less similar to the original compound. So I will set this Tanimoto score to 40. The rest of the options I will leave blank, and then start the tool. And then what this tool should do is it should take this SMILES string, which I showed you here, and it will search the Chembor database and return a list of compounds in the Chembor database which are chemically similar to the original SMILES string. Yes, so there are various options here. So you can filter also for approved drugs. This will probably result in a very low number of results being returned. You can filter for molecules which are considered to be biotherapeutic or natural products, or for this Lipinski rule of 5, which is a kind of empirical rule for which tells you how drug-like a molecule is likely to be. So you can feel free also to experiment with entering different parameters in this tool interface and seeing what kind of results you can get. So are there any questions so far? Is there anything which I should re-explain or
Yeah. As of now, like 14 persons are trying to do along with you.
Yep.
And I think if anyone got any questions here, please you can feel free to raise your hand and then ask the questions to Simon. Yeah, please. I think you can continue, Simon.
I think I'll continue. So this tool has completed. So we have 13 molecules which are returned, which is not very many, but
sorry to intervene, Simon. There is one question. Like
yep.
by the,
can
you specify active sites in Galaxy?
Yeah, exactly. So that's actually what we need to do for this docking. So we have our list of compounds, and we want to then dock them into a specific active site. So in maybe, I don't know, 10-15 minutes, and I'll get to that point in the tutorial and show you how you then specify this active site for the docking step. So yes, I'll discuss that in I'll discuss that shortly. So we have this list of compounds, which is obviously quite small for a docking study, but this is just a tutorial, so it's fine. Yes, and then I will rename the data set. So something like compound library from Kemble. And then the next step is preparation of the input files for the docking. So we have to prepare both the receptor and the ligands in our compound library. So let's start with the receptor. So for this docking, we will use this program Vina, and what it requires is the protein structure to be in this Pdb Qt file. So this is very similar to the Pdb file, but it has one extra column with the Steiger charges of the atoms in the final column, which isn't present in the Pdb file. So to select a Pdb file, we just take the protein Pdb, which we have here. So it's important to use this one and not the original Pdb file, which we downloaded from the Pdb, but this one which we have cleaned, so it doesn't contain any water molecules or any atoms from the ligand, which is bound, and then we can just start the tool. And we have to prepare also the compound library, so the ligands that we want to dock, and again we use this compound conversion tool, and we convert from SMILES to the SDF format. So SDF is more similar to the Pdb format, in that it contains not just the molecule represented as a graph, but it contains also the three-dimensional Cartesian coordinates of the ligand molecules. So you can just click on this output format parameter and type SDF. And then what is important also is to generate 3D coordinates here. So because these SMILES strings don't contain any information about the three-dimensional conformation of the molecule, it's important that we use this compound conversion tool to produce this information about the shape and the conformation that the ligand adopts in three-dimensional space. And the SMILES format also doesn't contain any information about hydrogen atoms, so about the hydration state of all the individual atoms in the ligand. So we should add hydrogens which are appropriate for a particular pH, and then a good choice is 7.4. So a neutral pH, and then we can just click on execute to start the tool. And in the meantime, this Pdb Qt file has been generated, so we can also then rename it to Protein Pdb Qt. Okay, so at this stage, once this tool completes, then we have our Pdb Qt file, which we use as input for the protein for the Vena tool, which will which would perform the docking, and we have our compound library in SDF format. So then for each ligand we have a list of coordinates, and in the SDF file then you have these. This is the separator, which indicates the point at which separates each of the molecules in the file. We have in total then 13 of these molecules in our SDF file. And the one thing which remains is the point which was already asked about in the chat, about how we specify then the active site for the protein. And we have a tool here called calculate the box parameters for an orthodox Vena job. So what this does is it defines a kind of box, so a space in which Vena will attempt to perform the docking of the ligands into the binding site. And what we can do as a kind of trick in this case is that we have our original ligand, which is from the Pdb, and we know that this is in the active site. This is often the case that you already have some crystallographic structure, so you know where the active site is, and therefore we can use the position of this ligand to help us to find the the center of this box that we want to define, where we dock the compounds into. So we select here our input ligand or pocket as this ligand Pdb file. So for the x-axis, we define 5 for each of the axes. So 5 for the x-axis, 5 for the y-axis, and 5 for the z-axis. And this defines the number of angstroms which the box will extend on each side of this input ligand. Then exhaustiveness is the number of times that the software will try and search this box to find these binding poses. And an 8 is generally a good choice, but we want to save some computational resources here because this is just a tutorial. So we set exhaustiveness to 1, and random seed. It doesn't matter what you set it to, but I think 1 is a good choice here. Let me press on execute to start the tool. And then you might say, well, and this is quite a nice tool if you know the position of some kind of compound which is in the protein structure, which you can use to define this box, this active site. So I saw already that as it just appeared as a question from Shivam in the chat. So I'm not going to show you this directly in the tutorial, but there's a section in here on how to find the binding site of a protein which doesn't contain a ligand. So we also have this tool in Galaxy, which is called fpocket. And what fpocket does is it searches the protein structure for pockets in the three-dimensional structure which are likely to bind small compounds. So you can choose what type of pocket to select. In this case, this is a good choice. And then you can select your protein B and Pdb file. And then what will happen is when you run this tool, is it will produce the Pdb file for each of the individual of the pockets which it finds in the protein structure. And this is described in the tutorial. That it produces then a list of these pockets. What you can do with this box parameter calculation tool is you can use not just a file containing the input ligand, but also the file for a protein pocket. So this allows you to be quite flexible. You don't need to know the ligand. You don't need to know the position of a ligand which is already bound, but the advantage is that it is a little bit more convenient, and it allows you to skip this step with the fpocket tool. So in the meantime, then this tool has completed. So this creates a very small file. It's a configuration file which tells the Vina docking software these parameters. So it tells it the center of this active site, which it should search during docking with X, Y, and Z coordinates. And it also specifies then the size of this box in the 3 dimensions. So in the X direction, the Y direction, and in the Z direction. And then seed and exhaustiveness are set to 1. Exactly. So then at this point we have our 2 files which we can use for the docking. The protein receptor file, as well as the list of compounds, and we have our configuration file. So I guess I will just pause again briefly and see if there are any questions, or if people need to spend some time to catch up, and then we continue and do the docking itself.
Yeah, thank you, Simon. There's a question from Shivam Pandit. What if we don't have a co-crystal ligand? Then how do we define the active site box?
Yeah, so I talked about that a little bit already. So then the idea would be to use this this F bucket tool, which can provide you with a bucket. And then there's another question as well about the for defining the active site of a protein for the generation of grid box. Is it reliable to consider the active sites which are predicted using the online tools and servers?
Yeah.
I guess I cannot give a definitive answer on this. In my opinion, then the best thing to do is to read the publication in which these servers were published, and to try and understand a little bit what their process is by which these active sites are being generated. And if this makes sense to you, then I guess you can trust it. And it makes sense also then to view the active site yourself and look if it is a kind of sensible size and shape for binding small molecules. So I would say that you can use these kind of software, but then also spends a bit of time to inform yourself and to check yourself if the results of the web server or the software make sense.
Yeah, please continue, Simon. Thank you.
Sorry, I was muted, but yes, I'll continue. So the next step is to do this docking with this autodoc Vino tool, and then so for the receptor we choose this Pdb file. For ligands, we take our compound library in SDF format. Ligand protonation we already specified in the previous step, but we can leave it as 7.4. And we want to specify a config file, which is here. And then we can run the tool.
Well, a lot of participants are actually not giving trouble to the Galaxy server. Only the 14 are doing, and actually a couple of jobs are queued in. And if you all use it, it would have been much more bigger problem. We would have seen a bigger problem. We lost the opportunity of seeing a bigger problem.
Oh, that's a shame. Yeah, so this tool takes a bit longer. I mean, this is the real simulation or calculation in this step. I don't know if there are any other tools in the meantime. If there are any other questions, I mean, perhaps then I can also continue with this optional section and demonstrate some of these tools which we have for example, for the visualization of chemical structures. So you can click on this visualization, select your compound library as SDF, and let's say that we display the molecular weight under the under the molecule, and then we can run the tool. So what this will do is just produce a simple figure which shows the all of the compounds in our library in a two-dimensional in a two-dimensional view. So it will look something like this effectively. And then we have some tools also for calculating fingerprints and dustering. Perhaps I can demonstrate these as well. So yeah, so for this we need to remove this second column here of this smiles file. So the best thing to do is to copy this smile string here, click on upload data, and paste data. We can set the type to SMI, so smiles. We click on start. I'll just rename it smile string. And then we can concatenate this with our compound library file. So we have a list of now all the compounds, including the ligand which we extracted originally from the Pdb file. Yeah, and in the meantime, then the docking has completed. So I don't know if you saw already today, we learned about collections in Galaxy. So in your Galaxy history, which you see here, then you have it's a kind of flat structure. So you just have a list of data sets. And what collections allow you to do is to introduce a kind of directory or folder structure in history. So you can click on this collection here, and it shows you a list of data sets which are contained within the collection. So you have then in this collection you have 13 different data sets, so one for each of the docked compounds. And then for each of them, then you have a different number of docked poses, which the software has successfully found. So, for example, if we look at this ligand 1, then it's the same compound in each case. So this chemical 178130. And so the structure is the same, but the coordinates will be different in each case. And what also Docfina does is it produces this score for docking. So here minus 8.3, then the second one is minus 7.8, minus 7.7. So scores which are below 0 indicate that there is an affinity between the ligand and the protein. So it's like with free energy, I guess, that negative free energy indicates that at the equilibrium, then the protein and the ligand will bind. So the molecule which is first in the SDF file is the one with the highest binding affinity in each of these cases. Yeah, it seems that the data sets which I started are kind of stuck. I see that there's another question about the best value to be considered for the hydrogen bond length between a protein and ligand interaction after docking. And again, this is, I guess, a bit subjective. I would say maybe 2.5 angstroms. But I think most software will allow you to specify this yourself, so you can also experiment a little bit. And then, of course, I guess you should not only consider the length or the distance between the hydrogen and between the hydrogen you're considering and the oxygen or nitrogen, but also the bond angle, but the bond angle, so a bond angle of maybe less than 30 degrees away from a straight line is probably a good idea, but the different, so yes, I guess that would be my kind of personal answer. So less than 30 degrees and less than 2.5 angstroms, but I think that there are lots of different ways to answer that question. I don't think that there's one single right answer. Yeah, I guess that will then just wait a little bit for people to catch up and see if there are any more if there are any more questions.
Yeah, please, any questions? You can raise or you can unmute yourself and then ask the questions, please. This is one of the most detailed and lucid talk. So it's important, like you get many questions, many doubts, especially the 14 participants who are doing along with Simon. It will be highly appreciable, and then it will be great learning experience that you can ask questions while doing your work.
Yeah, I mean, it's fine also if there are no questions. If something occurs to you after the talk, then you should also feel free to send the email or post in one of the chats, which I think Chris mentioned in the previous in his previous talk. But of course, any questions now are also would also be great. Yeah.
Yeah. Thank you, Simon, for that. Yeah. There is one question, Simon, in the chat. What is accuracy and efficiency of blind protein ligand docking? Simon, are you there? Simon?
Looks like we lost him again.
Okay. Yeah. I think we join in a few seconds.
Yes, once again, some problem with the connection. Sorry about that.
Yeah, please. There is one question, like,
Yeah,
what is
question
accuracy and
about-
efficiency of blind protein docking?
Yeah.
Protein ligand docking.
I don't fully understand the question or what's meant by blind protein-ligand docking. I mean, what I would say certainly is that docking scores are not that reliable in of themselves. So I would advise you, if you want to do some kind of docking studies, to that use the docking as a way to produce hypotheses. So you view them as potential binding positions, but then you also use some different method for the validation of the poses. So you have some insight into whether they really correspond to some experimental to some real experimental possibility. So, for example, I think Chris talked a little bit about the fragment screening, which on the SARS-CoV-2 main protease, which we've been working on. And there, what we are doing is we are taking compounds which are based on a set of input fragments, so experimental fragments, and then we are docking these compounds. And once we have the docked once we have these docked poses, then we are then comparing them with the original experimental fragments. So we can say that if the docked pose, which we get as an output, has some similar three-dimensional position to one of the input fragments, then we can say with some confidence that this pose is likely to be meaningful or have some or that we can rely on it. But yeah, I mean, I would certainly agree that just to do this docking by itself and to take the first one or two poses blindly is not likely to be a very good approach or very efficient approach. Okay. So in the meantime, then this visualization tool completed. So you can click on this view data icon and get maybe a little bit of insight into the structure of these compounds. So one thing which I notice straight away is that you have this resorcinal structure. So this 6-carbon ring with these two hydroxyl groups here, and this is a kind of motif, which is very common in compounds which bind to this HSP90 protein. And it was also present in the original ligand, which we got from the Pdb file. So yeah, it's quite interesting to see that that this motif is present in the in our compound library. Then in the meantime, we have got our concatenated data sets of our compound library with the initial
Simon, there is one question in the chat. If you can able to, yeah, please. Simon, are you around? Okay.
Yeah, sorry, again some issue with the connection. So I Yeah, so there was this question about checking the synergistic effects of two compounds by combining them in ChemSketch and the docking in Galaxy. I think that makes sense as an approach, especially if you know that the two compounds have some activity or some particular functionality that you want to use, and you can, like you wrote, you can try and combine them in ChemSketch and then to upload into Galaxy and to do this and to dock them into your protein of interest. I think that makes sense as an approach. And then what I would then say, like in answer to the previous question, is that you do this validation step where you then compare the results to the positions of the original compounds. If you have some three-dimensional information about their position in the binding site, as a way to do a validation of the results of the docking. So yes, I will share my screen again. Yeah. So there's this concept of molecular fingerprinting, which is used to compare the chemical compounds and to judge how similar they are. The idea is that we have a compound with various different functional groups, and then we have a bit string, so a string with which is made up of zeros and ones, and then for each position in the string, if a particular feature is present, then we set it to 1, and otherwise we set it to 0. And I'll just go back to the questions. Yeah, so there was that second part of the question which I missed about the if there's any tool for predicting membrane and BBB permeability of the compound to trace release kinetics. And yeah, unfortunately, we don't have such a tool. If you have some suggestion for software which can do that kind of prediction on the command line, then please feel free to suggest it, and perhaps at some point we can also integrate it into our platform. But yeah, at the moment, unfortunately, we don't have a tool for that. So yes, so in the end, for each of the molecules, we can calculate this kind of fingerprint. It will not work exactly like this with these 3 examples of functional groups, but in principle, then you have it works like this: that you have various features in the molecule, and the bit string encodes the presence or absence of these features. And the advantage of then extracting this information is that you can then perform some kind of clustering, and you can then judge the similarity or lack of similarity between your compounds. So we use the molecule to fingerprint tool for this calculation. We select 27, and there are different kinds of fingerprints in this case. So I'm not sure which is recommended in the tutorial. Okay, so just the default these FP2 fingerprints. So let's start the tool. And then what it will do is that for each of these compounds, then it will calculate a fingerprint which we can then use for molecular clustering and for calculating and for calculating the similarity of our compounds to the original lead compound, yeah, exactly, to cluster them and compare them to the lead compound. So if we view the fingerprint file, then it looks something like this. So it doesn't look like anything which is easy to read or to understand, but that's okay. So what you can see is that on these rows you have the chemical identifier from the chemical database, and then this is the fingerprint, which is encoded as a long numeric string. And then we can perform some different kinds of clustering. So there is this there is this Taylor-Butina clustering, which is used to cluster these molecules. So let's run this with a threshold of 0.8. Okay, so the clustering is completed. We then need to use this this second clustering tool to actually provide some kind of visual depiction. So we can use this data set here. Okay, and the threshold we can leave at 0.0. The format doesn't matter, but SVG is a better choice than PNG. And let's produce both of these outputs, I think. Then what we will get is some kind of plot as a dendrogram, which shows a hierarchical clustering of all the compounds in the compound library. Yeah, so hopefully this tool won't take too long. Are there any questions in the meantime? Anything which I should explain in more detail, or yeah, any general questions about molecular simulation or okay, it seems that the job has failed, so I will just try and rerun it. Yeah, so normally if you encounter a failure, then you can click on this view details icon here. And then it produces some general information about the tool. And then often it contains then these two rows, which contain the standard output and the standard error of the tool. But in this case, these are both empty, so I don't really have any clear idea about why the tool failed. So I'm hoping it's just some transient error, and when I rerun, then it will just then it will succeed this time. So let's see if that's the case. Okay. yeah, so this time then the error is looks a bit more meaningful. Here the line must contain an equal sign. Yeah, now I see what the problem is. I should have used, I've used the wrong data set as input for the tool. So I need to use this data set 28, which is which is FPS file, so the fingerprints, which I've generated from my compound library. So I'll try and run the tool again. I can remove these files. So hopefully it should succeed this time. Okay, this time it looks a bit better. So, I mean, that doesn't look so promising. Perhaps I should have set a different threshold. No, I'm not sure this doesn't really make sense. So what you have here is you have a similarity matrix. So we have 13 compounds. So we have therefore a matrix with 13 rows and 13 columns, and then each point in the matrix tells you how similar the compounds are according to this fingerprint measure. And for some reason there is some problem with the plotting of this dendrogram. So yeah, I'm not sure what is causing that, to be honest. But effectively, you should have some compound, some figure like this. So you have a dendrogram, which shows you, for example, that you have your original ligand here, and that it's quite similar to all of these compounds here with these chemical identifiers, and then these two here on the left-hand side are then very similar to each other, but much less similar to the ligand and to the rest of the compounds. And then there is this further investigation stage, which is optional, and I won't demonstrate that here, but you can play around with these tools and try specifying some different parameters as well. Yeah, so now I'll show you a little bit about post-processing. So we have this very useful tool, extract values from an SD file or an SDF file. So we have this file which was produced by all this collection that was produced by the docking tool. So we can submit it to our SD file, and then we can produce and what it will do is it will go through all of the molecules in each of the SD files, and it will check all of the properties which are specified in those files, and then extract them in as part of a convenient table. So you can then take these properties and you can you can make some plots or or filter based on these properties. I think it makes sense to include the property name as a header of the table, and to include the molecule name. And you can leave this field blank if you want to extract all properties, or you can extract specific properties by specifying a list of properties separated by a comma. So I'll press execute to start the job. And so what happens is that if you, we have a collection here, which we used as the input. So this Galaxy collection produced by the docking tool. And if we then run the tool on a collection, then it produces a new collection, and it runs the tool individually on each of the component datasets within the collection. So if we look now at this ligand 1, and then this is just one example of the output. So it shows that for this particular compound, that you have this this list of poses. So like we saw before, the top scoring pose has this score of -8.3, and then you also have these Rmsd scores, which tell you how similar the poses are to the most highly scoring pose. So these two have an Rmsd value of 0, because this is the most highly scoring pose, but the rest of them then have a different Rmsd score because they are more different. Then what we can do is we can also convert our SD files, which we produced back into Pdb format. So here we have to select as the molecular input file our docked ligands, and because Pdb files, in this case we want to choose this option, split multi-molecular files into a collection. So each of these SDF files in this collection contains multiple molecules, and we'd like to create a collection which then contains a data set for each of these individual molecules. Yeah, so what we actually end up with here is a collection of collections. So I hope this is not then too confusing. Yeah, perhaps this is a bad example. So I'll remove that example and just demonstrate on a single file. So if we click on compound conversion, then I can select just a single one of those files in that input collection. So I'll just select this ligand 1. I can drag to molecular input file and then convert to Pdb. And again, it'd be good to generate hydrogens at pH 7.4 I can press on execute. So yes, I missed this. Split multi-molecule files into a collection, so I'll press on execute again. And then this time it starts to generate this list collection. So what this will do is it will produce a list of Pdb files for each of these docked poses for this ligand. And then we can view this pose in using the VMD visualization. And what in principle you can do is you can concatenate this file with the original structure for the protein, and then view the compound as part of a hypothetical protein-ligand complex. Yes, so I think that brings the tutorial more or less to an end. I don't know if there are any more questions. I realize that I haven't used my entire time, but I'm happy to take any more questions from the viewers, or if there's anything which I should explain again, or yeah, please just let me know.
Yeah, any more questions, please? If there are no questions, I think, Simon, are we done? Or anything else you're trying to show?
No, so then we're done from yeah, as far as the tutorial is concerned. Yeah.
Okay, if there are no further questions, I take this opportunity to thank Simon. So detailed analysis on protein-ligand docking, starting the workshop series like 1, started with Simon with a lucid and clear step-by-step analysis, like starting from cheminformatics, what is protein-ligand docking, then separating protein and ligand structures, then a kind of hands-on that stepwise was being followed to show, and we've even witnessed around 14 students are trying to do along with him. That shows his clarity of thought and the work that need to be performed. Then he further showed on creating the processing of the compound ligands, generating compound library, searching from ChemMBL database, then further moving to preparing files for docking, then docking that's been performed by using the compound libraries which have been used, further visualization of the compounds, then calculating the fingerprints, and then clustering. And then looking into the endograms, I think there may be some technical issues there. That's the reason we could not able to see. And further we see on post-processing and plotting. So nice to interact with you, Simon. And any questions, like they'll try to contact you through your email. Yeah, thank you for your time. And before we leave, we'll just take a photograph, and I give turn on your video, please, so that we can have a video. Yeah, video image. Yeah, please, everyone. Simon, it will be great if you can able to stop presenting so that we can have a snapshot. Yeah, if you can stop presenting. Yeah. Kiran, could you please take a snapshot on your
Sure.
from your behalf?
Yeah.
Please. Yeah, please, everyone, request you to kindly turn on your video. Yeah, please go ahead. Shivam, like, yeah, everyone please. Shivam Pandit, Veena Rawat, Lipsa, yeah, Santosh, yeah, you should come forward. It's an opportunity that you basically share to keep your photo. Yeah, I hope everyone turns on the video, please. Yeah. 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 Give a smile. Yeah. It gives a lot of positivity. Okay. And ending up with a smile. Yeah. So we are closing a session with this workshop. Yeah, Kiran, now it is over to you. Yeah. Thank you, Kiran. Yeah. Thank you, Simon, for your wonderful session. Yeah. Thank you so much.
Yeah, thank you.
Thanks, Simon. Okay.
I think, Kiran, tomorrow,
Yeah,
if you can
exactly.
schedule
Yeah.
tomorrow's.
Yes.
Thank
I just shared once the tomorrow schedule. So thank you for all being here for today. You had a taste of one complete step-by-step procedure. Tomorrow you would have 3 more talks. Most likely they would also be in terms of the last talk what we had today would be a kind of more of step-by-step procedure. They are a kind of workshops, so you could always try to go, and there's the training links are also provided in the link what we said. So in the Bioclues link, you can actually visit that link and check out all the links, what were the trainings used by all the speakers today. And about the first workshop where the Vipin also showed, we will try to get the presentation so that you can also try to do that. And you can try, and you can also ask questions in the Gitter that will stay there. The questions people can come and then they can answer also later. So if you are trying to ask in the Gitter, the questions will stay there, and hopefully most of the speakers have the access to there, so they will be answering if required. And for tomorrow's, it will be you will have starting with a workshop 3, and then workshop 4 and 5. So it will be 10 o'clock start, a bit late start tomorrow. So you will have a bit more sleep. And after the first talk, tomorrow there is a lunch. So this is for the tomorrow session. If you have any questions still, we will stay until you all are here about regarding the using of the Galaxy, other things. You can ask any other question also right now. If you don't have any questions, then that's the day. That's it for today. But yeah, if you have questions, you can stay back and ask also. That's also completely fine.
Yeah, please. It'll be really good. Please stay back and then you can ask your questions. You might be having a lot of questions. Any questions regarding InBix and those kind of stuff, you can always stay back and I can ask your questions. Yeah, please. We are here for more 5 minutes. We're here. Yeah, please. If there are no further questions, yeah, thank you for attending. Yeah, see you tomorrow morning. Yeah, thank you, one and all.